All right, so welcome. Today is Monday, March the 8th. Okay, we are marching on in our quest to finish up with all of this AP stuff. Just scoot over here.
Or I can move this over
Yeah,
too.
just move that over.
You're good now.
Okay. So, we have today we're going to start talking about pH and the pH scale. We defined acids and bases on Friday. Again, on the definition of acids and bases, if it's an Arrhenius acid, it's a Bronsted-Lowry acid, it's a Lewis acid. They're not going to contradict one another. Now, as you go and broaden the definitions, a Bronsted-Lowry won't always fit an Arrhenius. But a Bronsted-Lowry acid will be a Lewis acid. Lewis just encompasses all of them, and they come up with some other crazy things, okay? So, all you're gonna have to know on Lewis is the definition and possibly being able to recognize, and that even then might be a bonus question, since it's not on the AP test. So, what if we talk about pH? Okay? And you're gonna have to come over this way.
Yeah, I got it.
Okay? pH, would anybody know what pH is equal to? Log something. The negative log of the concentration of the H3O plus. Now you could just as easily put H plus in there. What's the name of H3O plus? Hydronium, and that's not heavy water. Okay? The heavy water is made up with deuterium instead of protium. Deuterium has one neutron. It's got a proton, a neutron, and an electron. And so it weighs twice as much. So when you have deuterium oxide, D2O, if the molar mass is 20 grams per mole, not 18 grams per mole. And so that's very rare because 99.985% of all hydrogen is hydrogen 1, which we call protium, and only 0.015% is hydrogen 2, which we call deuterium. And then there's a man-made hydrogen 3, which is called tritium. Or tritium, I call it tritium, but tritium might be more accurate, I don't know. Seems to me like there's something, I've never seen any of the Spider-Man movies, but it seems like at some point when the original Spider-Man, the tritium is what he got bit and injected with to turn him into Spider-Man. There was something about that, I don't know. Anyway, so this one's radioactive. Too many neutrons, it's radioactive, and so it's used in atomic bombs, hydrogen bombs and stuff. And Spider-Man. Yeah. Okay. Well, that's why I had it affected his genetic makeup, we should say.
So did it affect my genetic makeup?
Probably not into a Spider-Man type thing, probably more into a dead, high risk of cancer type thing.
One way to find out.
Okay, that has absolutely nothing to do with what we're talking about. All right, I just can't help myself sometimes.
Martha's always gotta be there.
That's just a little Monday freebie for you. So pH is the negative log of the H3O plus. So what's POH?
Negative log of hydroxide.
The negative log of the hydroxide ion, OH minus. Okay? Now what is the relationship between pH and POH?
It's like 14 minus.
They add to 14.
pH plus POH is equal to 14. And that comes from the equilibrium expression for the autoionization of water, which is H3O plus times OH minus. Anybody remember what KW equals?
1 times 10 to the 14. Or negative 14.
Okay, equals 1 times 10 to the minus 14. So what that means is that when you just have a glass of water, it autoionization of H2O. So what is it autoionize into?
H3O and OH.
Who's on fire today? Okay? So what would be my equilibrium expression for this reaction? The H3O plus times the OH minus, right, is equal to K. So we call that KW, okay, the equilibrium constant for water, and it equals 1 times 10 to the minus 14. Now, what's the ratio of these two to each other? 1 to 1. So if I know that the equilibrium constant is this, okay, well, first off, let me show you how this one gets to this one, then we'll talk about the actual values and what the pH scale. If I take the negative log of both sides, okay, and then we're going to get rid of this, so I'm going to take the negative log of this, and I'm going to take the negative log of this. Well, when you have two things that are multiplied, what do you do with logarithms?
Add them.
So it's the negative log H3O plus the negative log OH minus. And what's the negative log of 10 to the minus 14 going to be?
14.
14. Remember, logarithms are 10 to what power is equal to that number. So 10 to what power is equal to 10 to the negative 14? Well, obviously negative 14, then we take the negative of it, makes it positive 14. So what's the definition of negative log of H3O plus? pH, POH equals 14. So this equation really comes from my KW equation. So KW, I'm going to put that back up over here. So this equation, this equation, this equation, this equation, everything you need to know about pH. Now, by the way, pH will only apply to areneous acids and bases because you have to have H3O plus, you have to have OH minus. Now, since this is an equilibrium, we have each of these, what's the H3O plus going to equal? What do I have to do? This is this times this, so it's really like x squared. Take the square root, what's the square root of 10 to the minus 14? 10 to the minus 7. So the OH minus is the same. So what's the pH going to be?
7.
The POH is going to be 7. We call that neutral. H plus equals OH minus. Okay? Pretty simple so far. Just building a foundation. Pretty soon we're going to start, building a frame. We'll have our whole acids and bases house. Now, because this is an equilibrium, if I add more H3O plus to the water, what's got to happen to the OH minus? It's got to decrease it because KW, whenever you have anything in water, the H plus times the OH minus always has to equal 1 times 10 to the minus 14. So if I put acid HCl into water, it's going to make this H3O plus go way up. What's that going to do to my OH minus? it's gonna go way down. So even in an acidic solution of HCl, a strong acid, you're still gonna have some, a very small amount, but some HCl. Okay? So, for strong acids, and we know our 6 strong acids, right? And you will have these memorized coming up shortly. We're in March. End of April is when all things memorized are memorized. I've been talking about them kind of all year long on different things you're just going to have to know. Okay? But the 6 strong acids, where do we find them? In this room. On the chart. So we look and we see HClO4, H, I, HBr, HCl, HNO3, and H2SO4. They probably should be in that order. Yes. Okay? So what does that mean about makes them strong? 100% ionized in water. Perchloric acid, hydroiodic, hydrobromic, hydrochloric, nitric acid, sulfuric acid. Do we need the names of those? And those are all acids. Just so you get comfortable with the names. Now, where are strong bases? We don't really use that so much for our strong bases. Now, the ones on the bottom, the conjugate bases, are very strong, but that's not really what we consider to be the strong bases. There's a little trick on the periodic table. It makes a B on the periodic table on the first column, a block lowercase b. Lithium, sodium, potassium, rubidium, cesium, strontium, and barium hydroxides. Okay, here's your B. And then go up. Okay, those hydroxides, they're only hydroxides that are soluble. If you look up here on the solubility chart on hydroxides, only ammonium, cations of column 1, barium and strontium are soluble. All the other ones are basically insoluble. So they're weak bases because they just don't dissolve in water, which means they don't break up into the cation and the OH. They just sit on the bottom of the water. Okay? So that's the only reason. If we could get them to dissolve, then you produce a bunch of OH. So these are the only soluble. So those are your 7 strong bases. They also are going to produce 100%. And yes. Now, technically, do we have to memorize? Yes, but I mean, if we just know where they're located on the periodic table, then it's a lot easier for those. This one's just straight up memorization. But these are your 3 hydrogen halides. Nitric and sulfuric we use all the time. Very few tests ever use perchloric acid, and anyway, I don't see that much. So we have lithium hydroxide, sodium hydroxide, potassium hydroxide, not strontium, come on, Steve, rubidium hydroxide, and cesium hydroxide. Then we have barium and strontium. Those 7. 2, 4, 5, 6, 7. Those are your only strong bases, the only ones that are soluble in water. Every other acid, every other base is going to be classified as a weak acid, a weak base. we're gonna have to do equilibrium problems to figure out how much actually dissolves and figure out what the pH is. But let's talk about doing the pH of a strong acid. Okay? So if I have HCl, I put that into water, what's it gonna make?
H3O plus CN1.
Okay? So if I put in 0.1 molar of this, initially, I have 0 and 0 here. Since it's a strong acid, what does that mean? How much of this is gonna react? So it's gonna be minus 0.1 molar. So this is gonna be plus 0.1 molar, right? Cl minus will be 2, but we don't care about Cl minus. That has just spectators just floating around not doing anything. So if I want the pH is nothing more than the negative log of 0.1, which is 10 to the minus 1. So the log of 10 to the minus 1 is 1. Take the negative of that, or negative 1, take the negative, is positive 1. So the pH of that solution is 1. Now what's the pH scale? 0 to 14, right? That's what we normally think. It really is way broader than that, but most of our acids fit the scale from 0 to 14. 7 being neutral, below 7, acidic. Now because it's a logarithmic scale, that means that pH of 5 is 100 times stronger than a pH of 7. Each time you go down 1, it's a factor of 10 because we're dealing with logarithms 10 to the certain power. Okay? So it's not like just it's a little bit stronger acid. A 5 is 10 times stronger than a 6. A 4 is 10 times stronger than a 5. So a pH of 1 is a pretty low pH. All right, so what about NaOH? And normally we don't include water with these. We're just going to say that they dissociate into Na aqueous and OH minus. The water is just going to kind of complicate things. So, if I put in 0.1 molar of this, what's my change going to be? Minus 0.1 molar. Because they all ionize 100% or dissociate. So, I don't care about the Na plus. This is the one I care about. So, can I find pH directly? What do I have to find? pOH. So the pOH is equal to 1, so what's the pH going to equal? pOH is identical to pH, but for some reason it's discriminated against and nobody cares about the pOH. We just want the pH. Okay? That's the favored one between the two. And so, but in any time you're dealing with a base, you have to first find the pOH, and then just subtract from 14 to find the pH. One extra step with a base. All right? Now what if we put in barium hydroxide? What's that going to dissociate into? Ba2 plus plus 2 OH minus. So if I put in a 0.1 molar of this, what's my change going to be? Still a strong base, right? Minus 0.1. But what's the OH going to be? Plus 2. So my POH is gonna equal the negative log of 0.2, which that one you can't necessarily do in your head. Does everybody know how to do a negative log on your calculator? .699. So notice that it's even lower pH, not double because it's a logarithmic scale, so it's not linear. But because we're getting 2 for 1, it's going to be a much higher OH minus concentration. All right, so pH is really pretty simple. I think you guys can work with the 4 equations, pH plus POH, pH plus POH equals 14, knowing the individual ones, and then our KW expression we'll use more and more as we get into equilibrium. I don't think, we don't really need to do any more practice problems of strong acids. That's why you have to know your strong acid, because there's no equilibrium. You just know however much of this you put in, that's how much H plus you have, because it's 100% ionized. So we can always just know our H plus with a strong acid, strong base, we know what the OH minus is, and then we just do real straightforward, easy problem. Of course, we probably won't have many of those, but you got to start there. Okay, so everybody good with the pH scale? We know below 7 is acidic, above 7 is basic. The farther away you get from 7, the stronger the acid, the stronger the base is going to be. Okay. I'm just going to throw these out and you can take them down. Some of the properties of acids. Okay? Properties of acid. I've never seen an AP question asking about any of this, but it's just kind of good to know. Acids taste sour, but you never, ever, ever want to use the taste test. And in that little excerpt you're going to read, it talks about how they used to use the taste test to determine something's acidic or not.
That's a good point.
Yeah, until the tongue has issues. Okay, so they all taste sour. So if you have a food that has a sour taste to it, even like citrus fruits have that combination of citric acid, sour, and then the sugar is sweet. But if it's not really ripe yet, it tastes more sour than sweet. Okay, Granny Smith green apples have maleic acid in it. That's what makes the sour flavor of that. Milk goes, the lactose sugar changes into lactic acid when it sours. And so just anything that you eat that has a sour taste is more than likely going to be some kind of acid present. Okay? Obviously acids neutralize bases. Acids affect indicators. What's an indicator? Changes color according to pH, right? So litmus paper is the most common. What color is litmus in an acid? Red. What color is it in a base?
Blue.
Blue. BB, blue is basic. Okay? And then, of course, we know our 6 strong acids. So it's bases. If acids taste sour, what do bases taste? Bitter. Bases taste bitter. Soap are made from bases. Back in the day when you could discipline your kids, if somebody had a dirty mouth, nowadays, I mean, it's amazing, the language. The F-bomb is just so common now, and everywhere you go, and that was like, oh my word, I can't believe somebody said that word in my day. If you said any kind of cuss word, you would get your mouth washed out with soap, because you had a dirty mouth, okay? And that soap just tastes bitter. It's not poisonous, it's not gonna kill you, it's not gonna do anything except taste nasty, okay? And so you get your mouth washed out with soap because of that bitter taste, okay? Obviously bases dissolve, neutralize acids. Acids neutralize bases. Bases also react with indicators. But bases dissolve grease and grime. That's why soap is made out of bases, and Drano is nothing more than sodium hydroxide with some magnesium in it so it gets hot, and then just kind of bubbles some, but it's dissolving all that junk that's down in the drain, okay? So cleaning, Windex has ammonia in it, which is a weak base, just to kind of help dissolve all the little, grease or whatever forms on a window. All right, so that's just some basic characteristics, some simple characteristics of acids and bases. All right, let's now just talk about what makes an acid strong or weak. So we have two types of acids. We have a binary acid, which is just HX. That's your HCl, HBr, HI, H2S, okay? For a binary acid, again, what makes an acid strong is its ability to donate, break up, get the H plus out of there. Can water break this H plus away? So the weaker the bond between the H and the X, the stronger the acid. So for binary acids, bigger is going to be a longer bond length. It's going to make it easier okay? So that's why when we're looking at our hydrogen halides, HI is listed higher than HBr than HCl. Because HI is down at the bottom, it's got the longest bond length, therefore it's the easiest to break. Most of the time, when we think about acids, we want to talk about electronegativity, but electronegativity is really a secondary factor. The size of the atom and the strength of that HX bond is what makes a binary acid stronger than another one. Okay? Now, I'll do it that way. A secondary factor, and I really want to stress this, that you don't look at this first. This is just kind of like if there's a tie or you're looking and there's just a secondary condition. Why would the more electronegative, stronger the acid, why would the more electronegative one affect the acidity? If I have a highly electronegative X, what's that do to this bond?
It makes it stronger.
Well,
It Does it make the H like want to go away?
Why? I'm looking for what type of molecule form? If this is a highly electronegative element, such as foam call, it's going to be polar, which is going to make the hydrogen very positive, which makes it easy to be removed by the water because it's going to have a much stronger attraction to the water. The more polar this bond, generally the easier it is to break. Now, but that is secondary because that's opposite chlorine, fluorine, chlorine, bromine, iodine. Iodine's the least electronegative, fluorine's the most electronegative. Okay? But when you're comparing HCl to H2S, okay, the size is pretty close to being the same, but because chlorine is more electronegative, it's going to be a stronger acid than H2S. Okay? So we want to look at the size first. And then if they're kind of close to one another, then you look at the electronegativity. The more electronegative one will be the stronger one, but that's secondary. All right, so now we have oxyacids. What do you think an oxyacid is? It has an oxygen in it. It's going to be HOX. That's what HClO4 is an oxyacid, HNO3 is an oxyacid, H2SO4 is an oxyacid. You have a nonmetal, oxygen, and hydrogen. Now, in this case, the greater the hydrogen to oxygen ratio, let's change it the other way. Oxygen to hydrogen ratio, the stronger the acid. Now let's just compare on this chart right here. The oxygen to hydrogen, it's 4-to-1. Here it's 3-to-1. Here it's 4-to-2 or 2-to-1. This is the strongest, then this one, and then this one because of the number of oxygens. These oxygens act like electron withdrawing groups. So we have ClO, and remember the hydrogen is always going to be attached here. So what's going to happen is this is pulling the electrons in. All of the oxygens are what we call electron withdrawing groups. They're all pulling it away, and poor hydrogen's being kind of left out here. Just everybody's, taking his electron. The chlorine is highly electronegative. The 4 oxygens are highly electronegative. Everything is pulling the electrons this way. More electron withdrawing groups. So, very easily ionized, 100% comes off. It's a very strong acid. Now, if I go to HClO3, now I don't have as many as electron withdrawing groups. HClO3 is right on the cusp of, some books call that a strong acid. Okay? But if we go to HClO2, now there's only 2 electron withdrawing groups, and so now it's not nearly as strong of an acid. So it's that high oxygen to hydrogen ratio that's going to tell me the strength. All right? But in the same thing, since this is all pulling the electrons away from this oxygen, it's always an oxygen to hydrogen bond, but the more electronegative this one is, the more electron withdrawing it's going to be. So the more electronegative the nonmetal, the stronger the acid. Okay, and up here you might want to just put HClO4 is greater than HClO3, which is greater than HClO2, which is greater than HClO. That's just in terms of the hydrogen to oxygen ratio. Here, what we'll say is that HClO4 is greater than BrO4, which is greater than HiO4. Because now see, the size of the central atom isn't a factor because the bond that's breaking is always the OH bond. So this is all electron withdrawing. And when we come, we're not done, but when we come back from the break, we'll look at some practice of these and being able to identify the stronger ones. Okay, so if I just have ethanol, this OH bond right here, it is polar, but it's relatively stable molecule, hydrogen, oxygen, okay? But so this pretty much is neutral. The hydrogen is not ionizable to any extent at all, okay? So it's pretty much gonna be a neutral, non-electrolyte, just dissolves as the molecule. But if I go and I change that and put an oxygen up here, now this is acetic acid. It's really called ethanoic acid. That's the official name. We call it acetic acid. Because of this extra oxygen, it's more electron withdrawing, makes that more positive, and so now it makes that hydrogen ionizable. But not extremely. This is a weak acid. Most of the acids in foods that we were just talking about have this carboxylic acid group. Okay? COOH. That's on any organic acid. It's going to have that COOH, and this is the H that's going to be ionizable on this O. But the more electron withdrawing groups we can put on there. Okay? So now we could go with, is it 5 after? No?
It's 2 after.
I don't know if they have bells today or not. They're doing all kinds of testing. I think that's over though. Nope. So now if I have chloroacetic acid, now chlorine is a highly electronegative element. It's going to be more electron withdrawing. It's going to make this even more polar because it's going to help pull the electrons this way. If we go to trichloroacetic acid, it's going to be much, much stronger because now we have many more electron withdrawing groups, pulling the electrons away from this, making this more polar, more ionizable, thus making it a stronger acid. That's probably the best term, is more ionizable. Okay? Now, one last thing on this. If I wanted to compare with which one do you think is the chlorine going to have more of an effect on? The top one. Why?
Closer.
It's closer to the H to have a greater effect. The farther away it gets, the less effective, the less, effect it's going to have on this one. Okay? So we have to look at the electronegativity, how many electron withdrawing groups there are, but how close they are to that ionizable hydrogen. Okay? You guys are looking so excited this morning. This is some good stuff. Okay, so we're going to take a break. And then when we come back, we'll look at some practice of these. Okay, and then get into actual acid-base equilibrium.